Dr. Chen, you have 20 minutes for your presentation. Please, at this time, the floor is yours.
Good morning, everyone. It's my pleasure to introduce what we have done in China based on the Chinese seismo geomagnetic monitoring rolling arrow. It will include the four parts. The first part, I will introduce the geomagnetic field. And then the second is the problem we faced. And then the third one is what shall we do? At last, I will show some results we have. The geomagnetic field is one of the basic geophysical field. You can imagine there is a bar magnet inside the Earth, and this bar caused a dipole field, just like this, surrounding our Earth. Geomagnetic field is a volcano field. We can use three independent elements to describe it, and we can calculate the others element from these three independent elements. The three elements can be x, y, z, or dhz, or f, total intensity, declination, and inclination. And please attend that XYZ is different from normal system. The X is point to north, and Y is point to east, and Z is point to down, is point to the center of Earth. Here is the function. This function describes the relationships between these elements. Of course, the source of the geomagnetic field is different. The field can divide three parts. The first part is internal field. The internal field can be also divided two parts. The first one is the main field, also called the core field. This is caused by the core and mantle boundaries liquid, and the second part is the source field, also called the crustal field, and the others part is external field. This part is caused by the current in the ionosphere and the magnetosphere. And the third part is induced field. Here is the internal field spatial distribution. This is a total intensity. In north or in a higher latitude arrow, the total intensity is a higher value, and in lower latitude arrow, the total intensity usually have a lower value. And there is the spatial construction. Here is like X. The shape is here. Temporary character of geomagnetic field. This is a recording of four observatories. The left part is the horizontal component, and the right part is the vertical component. And from down up to down, there's four observatories recording. The first one is Dedu Observatory. His location at north east of China here. And the second is Guangzhou. He is here in the south of China. And this one is Lasha. He is here in southwest of China. And the last one is Urumqi. He is here in the northwest of China. The main character we can find is the even this observatory have long distance, but they appear the seminal character of time series. And for example, from Guangzhou to Lhasa to Urumqi, their vertical components is increased directly, but there's still some little difference. For example, here and here, and this character also in horizontal component is reduced in all these four observatories, and also have a little difference here and here. So let's make character of the geomagnetic field variation. So they have the signal in a very large arrow, but have each location have there some little difference. Where analysis object is the source field, because the source field was caused by the rock's susceptibility, and the susceptibility can be influenced by the composition, size, and the pressure and temperature of these materials. If we monitor the source field magnetic field, we can get the variation of pressure and temperature, and then based on this, maybe we can get some information about the abnormal and then predict earthquake. That's our idea, and in this is our arrows point in China, and each point is one station. We use the three type of instrument to measure the geomagnetic field. The left instrument is called a proton meter, and this instrument can measure total intensity. The instrument in the middle is the DI meter, and this instrument can measure the declination and the inclination. Here is GPS. This instrument can get the location, the position of our stations, and this instrument also help to measure the declination. As our object is the source field, but the value we measured include all this part. So we have to remove the others, main field, external field, and induced field from our measured value to remove the others part, and we get the source field, just what we wish to. This as an example to show why it's hard or difficult to do. This is the time series of Dedu observatories. This is vertical component time series, and we can think we measured one time in here. This is here, and after 1 year after, we measured again here, when zoom in this part and zoom in this part, just like this, and this. So we cannot manage these two values, because this variation include the secular variation. It's the variation of main field. This is just like this. This part is called the secular variation. We have to remove this part, remove main field or core field, and the others here every day have the dual variation, just like this. Here is one day, yeah, the second day, the third day. Every day have a dual variation, like this time also. But every day is different. It's hard to get the very exactly the character of dual variation. And the frequency, there is some disturbs of the magnetic field. So it's hard to remove the dual variation like this. So that's the problem we faced, and we have to do to remove. So that's the problem we faced. We need to get the change of the source field magnetic field with very less value. But the system is very complex. Here is complex spatial distribution, and here is also has a complex temporal variation. How to do that? So we just first to look at main field. The main field has the character is that the his its special character is a long wavelength. So you can see the spatial distribution of main field. He had the long wavelength is very long. So this is the distribution. And for the temporal variation, there is also the spatial wavelength is longer, and also the temporal period is also longer, not just is long. So it's easy. It's easy to draw up the main character of the main field. Based on this realize, we use the holding data on the observatories uh, in China or surrounding China, and use the NOC method to build a model and to draw out the main field. The for the external field is harder to get the actually external field, and this is uh, two uh, two time series of two observatories. The up pictures is vertical component. The lower is the horizontal components in the same time, and we can say the dual variation is hard to get the same character for every day. It's harder because every day is different. Every day is different, and sometimes it's frequency. Frequent there is have a magnetic storm. It's disturbs. So it's hard for us to draw a model to describe external field exactly. The main character of the external field we realize is in temporary the period is short. It's short, and in spatial the wavelength is long. Is realized as we can do the spatial fitting and interpolation every minute we will do this fitting every minute and based on the data on let our data processing we need need to, based on the minutes data from observatory, to remove during variation, to remove external variation and external field. And we, based on the only data from observatory, to remove circular variation, and then remove the main field, and then do the interpolation, and then to get the variation of the source field. That's our data. Here is some pictures as an example what we have done, the variations of the source field magnetic field, and this is a control of different elements. And here is the horizontal arrow. This one is another useful picture to help us to find which well is abnormal, and this picture can describe the horizontals components intensity and direct result. And there's two earthquakes as an example. There is the variation of horizontal component. This is the length of this arrow describe the intensity, and also the arrow can describe the direction. And from the south to north, near the earthquake, the variations looks like stopped by something near the earthquake. The earthquake here is 6.5, and this earthquake magnitude is 7, and it looks like also stopped here. The intensity or variations have very light near the earthquake. It's also, but far away the earthquake, the variations have bigger intensity, bigger value. It's like this. We call this the variations value is very light, is abnormal. Here is the value is near the zero. Here about the relationship earthquake and the zero. Here is two new earthquake, very new earthquake in August, and this area is in North China here, and we use the right curve to describe positive, and the blue is negative, and we use the black curve to describe zero. So you can see these two earthquakes exist on or around zero, and this is total intensity. And this is horizontal. Here is there is also two zero cover near the earthquake here, and component is also very near the zero cover for all these two earthquakes. So if we put all the zero cover or the zero variations arrow together for the three elements, we just choose the all elements to disappear the less variation or zero variation arrow. We just pick this place, this arrow as abnormal. We just do statistics to find how many earthquakes. If all earthquakes or most of earthquakes disappeared this character, we collect 35 earthquakes magnitude bigger than 5 and we can say for all the elements, half earthquakes very near the zero, because the distance is less than 15 kilometers. This is the result from the laboratory, and we can use the machine to push the rock, and we measure the pressure and the susceptibility, and you can think this y-axis is the resourceful magnetic field, and we can say when pressure is in a high condition, the variations of the source field magnetic field, the variations become the rate become less, and in a lower pressure, the variations rate is higher. So that means less variations the source field maybe means higher pressure. And there's another result also, pressure the rock in a room, and as the push, the pressure increased again and again. But before the broken, the change of pressure become to zero before the rocks broken. So that maybe means variations of pressure is zero. The pressure is variation zero. That the source field, the magnetic field is also zero. So that's also support our that's conclusion based on geomagnetic data from observatories and our arrow. We can find pressure change and locking, and this change may be caused earthquake, and also cause the variations of the source field magnetic field, and this variations weak variation can also have some relationship with earthquake. That's all.
Thank you so much, Dr. Chen.